What's going on, everybody? This is Mr. Diamond, and welcome to Chapter 2 of Advanced Chemistry. Chapter 2 is going to be all about solutions. Now, I haven't at this point decided whether or not, due to the incoming snow day, if you're doing this before we have done the test or after. I'm leaning towards doing the test digitally. So you're probably doing that on Monday and then watching this, or on Tuesday and watching this on Wednesday. But just in case, if not, if I haven't made that decision, then we'll probably be taking the test whatever day we end up coming back to school. So I really don't want to do that, though. So I'm assuming that's what's happened. But we are now moving past redox, I think, and going into solutions. Section 1 is just, well, we need to figure out what these things even are. So this little bit is probably a bit of a refresher for some of the stuff you may have covered in previous science classes. I don't think we really had time to get to this in chemistry last year, so this is probably not familiar from my class, but maybe from one of your other classes. This is a refresher over mixtures. All mixtures have the following characteristics. They have to be made out of two or more parts that are physically combined and can be physically separated. If separated, the parts have to retain their identity. The composition from mixture to mixture may vary. It can be heterogeneous or homogeneous. And there are three major types of mixtures: solutions, suspensions, and colloids. And then we're going to define each of those as we're going through. Now, heterogeneous mixtures are, if you think hetero means different, they look different throughout. You can kind of tell them apart, just the pieces of them. Trail mix is like the go-to most common example that is used for a heterogeneous mixture. When you look at a piece of trail mix or a handful of trail mix, you can identify all of the different parts that are there. They are physically combined together. They are in the same location, but you can separate them apart physically. You can pick out the almonds and the peanuts and the whatever else is in your trail mix. And the parts also retain their identity. The almond is still an almond, whether or not it is in the trail mix or out of the trail mix. The composition can vary from mixture to mixture. One handful of trail mix is going to be completely different than another handful of trail mix. You're never going to get exactly the same thing. But getting to the homogeneous and then getting down to these guys down here, we're going to get a little more scientific. Obviously, here in chemistry, we don't do research involving trail mix. That's not really a thing that we do. So solutions, suspensions, and colloids. Well, first we have solutions. Solutions are homogeneous mixture. So if hetero meant different throughout, homo means same throughout. A homogeneous mixture of two or more substances, all in a single phase. So the important part about a solution is that they have to be within the same phase as each other, meaning they're all solids, they're all liquids, or they're all gases. It has the same composition and properties throughout. So in a solution, it will be homogeneous, meaning that you can't tell any different parts of them. The two components of a solution are a solute and the solvent. Solute are anything that is dissolved in a solution, or in some other cases, it's the thing there is less of. And solvent is the thing that does the dissolving or the thing there is more of. They can be composed of different states of matter, though. For example, we're going to make some pennies into brass, I think, if we have time in class. If not, I'll maybe post a video of it. I'm not sure yet. This whole next week is up in the air. Jello is an example of if you have just pure Jello, that's a solid, but it is a solution. It's a mixture of gelatin and sugar and all of that stuff that looks kind of the same throughout it. Air is the most common example that I usually use. This air right here that's in front of me and the air that's right in front of you is made out of a whole bunch of different types of gases, predominantly nitrogen. So nitrogen would be the solvent in that case, but then water vapor and carbon dioxide and carbon monoxide and all of that other stuff would be the solute, the stuff that there is less of. Kool-Aid is another example, but the pennies into brass also gets into the solid. The other way it can be a solid, which is something like metal alloys. Metal alloys where you can't see the two different pieces of metal, that's going to be a solution. So what about the other two then? Well, a suspension is a mixture that has particles so large they will settle unless constantly stirred. Sandy water, muddy water, blood, salad dressing. The example I have is this jar right here. It's got a whole bunch of glitter, and if I shake it, everything is kind of suspended and mixed throughout it, but if I wait for just a few moments, it's going to slowly start settling down. And I have to constantly keep shaking it in order for it to stay suspended. It is suspended inside of that suspension. Blood will settle into plasma and then your red blood cells. Sand will settle to the bottom, and mud will settle to the bottom if you have water. Salad dressing has the oil and the water. So again, doesn't have to be solids and liquids. This is a liquid, and if I shake it, it is currently a suspension, and then as I leave it to settle, we can kind of see that slowly this top is getting to be more yellow because the oil is starting to settle to the top or come to the top. Now, colloids they're just dumb. We're barely going to use them. Colloids are mixtures that have intermediate-sized particles, meaning they remain in a suspended state without settling in the same way as a suspension. Emulsions, foams, and gels are the three things that you'll hear for talking about colloids. But there's a couple of other ones, like fog is a colloid. It's water particles in air. Emulsions like mayonnaise are examples. There's fat and egg pieces and stuff like that, and all those particles are suspended together. They are big particles, but they obviously don't look uniquely different, or they don't look different throughout. Shaving cream, whipped cream, most types of gels, all of those are examples of colloids. They're hardly ever going to come up because it gets really specific. For example, like if I asked you what was milk, well, normally to us it looks like a solution. You can't tell it's different throughout, but it's actually a colloid unless it's unfiltered or unhomogenized, in which case it is a suspension. So you have to get super specific as to what it looks like, and it can be a little misleading. So colloids usually don't come up. I usually try to keep it very clear as to which one of these things that we're talking about. Now, the best place for us to begin in the solution process, or when talking about solutions, is how do these things form? How do they actually come about? And you might be thinking, well, it's this. Like there's a solute and there's a solvent, and they form a solution. They mix together. Like you stir the Kool-Aid packet in the water. Bam, solution created. Obviously, it can't actually be that simple because this is chemistry class, so everything has to be super difficult. They're actually created in three distinct steps. So first is that energy needs to be used to separate apart the solute. If you think of this as like the water molecules are packed to a certain density, and energy needs to be used to separate those solute particles apart. Or I guess in that case, that would be a solvent, which is step 2, which is the same thing. But those water molecules that are all bound together, there need to be some amount of energy to break those hydrogen bonds and allow it to form gaps in there. And then when you add the Kool-Aid or the sugar cube or whatever you're dissolving, those things are also tightly packed, and the energy needs to break those things apart and separate them. Because if there's not spaces, otherwise it would be like me saying, oh yeah, I'm going to mix together a solution of these pens. And then I just bang them together, and then no, there's not space. I would have to separate them into their components so you could mush them together. Unfortunately, I don't have like Dr. Manhattan-esque superpowers where I can separate a pen down into its atoms and then fuse them together. But when we're talking about things dissolving in liquids, it actually works that way. You can have the sugar cube that you drop in, it starts as a solid, but then as energy is added to the system, it begins to separate out, the water does, and then that allows the solvent particle or the solute particles to also separate apart. Then for phase 3, the solute and the solvent particles intermingle, and they combine together, and that releases some amount of energy. Remember, energy gets released by chemical reactions as kind of like a sigh of happiness or a jump for joy. Whenever a reaction is finished or energy has been kind of settled, it will release energy. So this step takes energy. This step takes energy. This step gives you back energy. That allows us to come up with an actual equation. The energy for a solution to form is equal to the energy required to break the solvent, the energy required to break the solute, so the solvent and the solute, so those two added together, and then you subtract whatever energy you get back at the end from it being released. So to represent this energy, we use the letter H. This stands for enthalpy, which we may talk about later. Even though it is technically what we're talking about now, enthalpy is kind of its own special thing in chemistry. I doubt most of you have heard of that. But we just, for now, just remember it stands for H. You can think of it as heat. It's not what it is, but if that helps you, you can kind of think of it as that. It's not technically that. Anyway, if the energy you need to break the solute and the solvent apart is less than the energy released, we call that exothermic. So like, let's say you put in 50, you get out 200. That 200 that you release is going to have to be given off in the form of heat, so we call that an exothermic reaction. Energy is exiting, heat is exiting the reaction. If energy is needed to break the solute and solvent is more than the energy released, though, we call that endothermic. If you put in 50, and you get out 50, you've lost 50, or you didn't get enough of that energy at the start. The end is not going to continue fueling the process. So outside energy will have to be put into the system to allow it to continue. And so since it's having to come from outside, it is entering, or endothermic. It is going to actually be a cold reaction, normally because it's sucking the heat away from the outside. So endothermics are chemical reactions accompanied by a gain in heat. Think of it as entering. Exothermic is a chemical reaction accompanied by a loss of heat. Think of it as exiting or leaving the reaction. And then for endothermic, the change in heat or the change in all of those energies will be positive, and exothermic, the change will be negative. So an example of what this would look like in a problem form, the energy of solvent to solution dissociation are 125 kilojoules per mole and 327 kilojoules per mole. So, and you don't really need to know which one goes with which. We'll assume this is solvent with a solution. Energy released from the formation of the solution is 500 kilojoules per mole. What is the energy of solution? Is this reaction endothermic or exothermic? So literally all you're going to have to do is add these two things together. So that would be 452, I believe, 452 kilojoules per mole minus 500. So the energy we're getting out at the end is more than the energy that we're putting in. I believe that means that we would have a negative 68 heat of solution, which means that we will get back 68 kilojoules of energy per mole, which means that this is a exothermic reaction. 48, sorry. My math that bad? Oh yeah, 48, not 68. I went the other direction. Anyway, I tried to do it in my head. I didn't want to have to do a whole video of just me writing out this example. But 125 plus 327 minus 500 gives you negative 48. A negative number here, negative heat of solution, tells you it's exothermic. There's extra 48 kilojoules that aren't being used for anything in the reaction, so it's going to go out and it's going to come off in the form of heat. So what if we wanted to speed up the rate at which something goes from solid to aqueous and keep the solvent and the solute the same? What are some things you can think of that may help something dissolve faster? Again, we're not going to make something dissolve that wouldn't normally dissolve. We're just trying to make it dissolve at a faster rate. Well, there's three main scientific ways, which is increasing agitation, increasing surface area, and increasing kinetic energy. But in normal non-scientific speak, we can stir something, we can break something up into smaller pieces, or we can heat it up. So stirring things or increased agitation causes more solvent particles to come into contact with the solute particles, and also you're adding more kinetic energy, which is allowing them to kind of have more energy in the system to break the bonds apart if they are having trouble with that, or doing it at a faster rate at least. For increasing surface area by breaking it up, if you increase the surface area, you're allowing more of the solute to come into contact with the solvent at a given amount of time. If you think of like a sugar cube versus like the same amount of sugar in a spoonful, when you drop that cube in, only the outside layer of that cube is actually going to get exposed to the solvent particles at any given time. So it's going to have to eat away at that outer layer, then eat away, then eat away, then eat away, and slowly go through all of those pieces before it's going to be able to do anything. But if it is, for example, a teaspoon of sugar, though, all of those individual sugar pieces are able to be surrounded by the solvent particles at one given moment. No individual piece of it is kind of locked inside of the rest of the sugar, so increasing surface area will increase the rate at which it will dissolve. And then also increasing kinetic energy or heating. I mentioned this kind of with the agitation. That's an example of a small amount of kinetic energy being added to it. But this is really the way that you can add like a lot more energy to the system. The higher the temperature, remember, temperature is a measure of kinetic energy. It's not actually a measure of heat or cool. So the kinetic energy of the particles is going to increase, meaning again, it's going to do the same thing, but increasing kinetic energy is going to make it happen faster, like this very fast gentleman right here who's just like going away at this paperwork here. So increasing the temperature is literally like hitting the subatomic fast forward button. As long as you don't increase it to a level that it starts messing with the chemicals involved, you are literally saying, okay, do the same thing, but every time you add heat to it, you're saying do it a little bit faster, or a little bit faster, and a little bit faster, and a little bit faster. And and that's going to cause the reaction to occur faster because you're again literally hitting the fast forward button on the atomic level. All right, that takes us to the end of section 1. I don't actually think there's a worksheet that goes with this one. Don't be mad at me, though, if when I check back that I'm wrong about that. I think you have a worksheet that will be coming up for stuff in this next section here, though. This is a pretty long video, so I am probably going to give you a couple of days to be able to write this down, probably 2 days to get this all written down. I think that's what I have written. Yeah, it'll take about 2 days for this. In the meantime, though, this is Mr. Diamond. If you have any questions, please shoot me an email. Otherwise, have a great rest of your day, everybody.